Okay, we'll go ahead and get started. Can everyone hear me okay and see my computer screen?
Yes.
Thank you. Well, I hope everybody's staying safe with the weather and hanging in there from that. What I'd like to do today is I'd like to review the quiz 2 answers. So that was the quiz you took last week. I'd like to go over those answers and then just remind everyone that the answers are posted in Canvas. And then we'll go and we'll continue on talking about chapter 14, which is kinetics. And then the final thing I want to remind people of is we'll finish off chapter 14 on Thursday. And then next week, next Tuesday, we'll have an exam, our second exam, and that'll cover chapters 13 and 14. Okay, so the first question of the quiz was the phrase like dissolves like refers to the fact that, and the answer was polar solvents dissolve polar solutes and nonpolar solvents dissolve nonpolar solutes. Number 2, when solutions of strong electrolytes in water are formed, the ions are surrounded by water molecules. These interactions are described as a case of, and the correct answer was hydration. Number 3, an unsaturated solution is one that, and the answer is has a concentration lower than the solubility limit. So unsaturated is lower than the solubility limit. Saturated means you're at the solubility limit. And supersaturated would be you're above the saturation, the solubility limit. Number 4, which one of the following is the most soluble in water? The answer was CH3OH, which is methanol. And the key to getting this one correct is, goes back to that question 1, like dissolves like. Water is very polar. So we're looking for the most polar molecule. And we think of it as the OH portion is the polar portion of the molecule. The CH3, CH2 containing portion is nonpolar. And so because of that, the CH3OH has the least amount of the CH3, CH2 portion. And so that makes it the most polar and thus the most soluble in water. Number 5, what's the concentration in ppm, parts per million, of a solution which is prepared by dissolving 15 milligrams of sodium chloride in 200 mils of water? So we know that if we're talking part per million or weight percent or parts per billion, that what we want to do is we want to get it expressed as grams of solute divided by grams of solution. And then we'll multiply it by whatever the correct factor is, depending upon which one of those we want. So if we have 15 milligrams of sodium chloride, we need to convert that into grams of sodium chloride. So we need to remember that the ratio is 1,000. And so 15 times 10 to the minus 3 grams is the same as 15 milligrams. And then the density of water we should know is 1 gram per mil. And so 200 mils of solution, 200 mils of water, if you're just adding 15 milligrams in, it's pretty negligible, that other weight. So essentially you have 200 grams as your mass of the solution. So we have mass of the analyte divided by mass of solution. And then because it's parts per million, that is 10 to the minus, 10 to the sixth that we want to multiply by. If it would have been weight percent, it would have been 100. If it would have been ppb, it would have been 10 to the 9th. So we go ahead and do that calculation and we get 75 ppm. Number 6, as the concentration of a solute in a solution increases, the freezing point of the solution decreases and the vapor pressure of the solution decreases. So for these two colligative properties, as we get more solute particles in the solution, both the freezing point and the vapor pressure go down. Number 7, what's the concentration? And we want that expressed in molarity, so moles per liter of HCl that's prepared by dissolving 25.5 grams of HCl in a 20-liter volumetric flask. So a few things we need to remember. One is we need to remember that molarity is moles per liter. So we're going to want to change that 25.5 grams of HCl into moles of HCl. And to do that, we need to calculate the molecular weight of HCl, and that comes out to be 36.453. So 25 grams of sodium chloride, or rather HCl, times 1 mole per 36.453 grams. That gives our numerator in moles. The volume, 20-liter volumetric flask, that's already in liters, so we don't need to do anything to that. So that 20-liter value is in the denominator. And so if we go ahead and do the calculation, we get 0.0350 molar. Number 8, we're told, so we're saying concentration of urea and the molecular weight of urea is 60 grams per mole in a solution prepared by dissolving 16 grams of urea and 39 grams of water is what molal? So remember molality is the small m, and the units on that are moles of solute per kilograms of solvent. So in this case, the solute is the urea, the solvent is water. So we need to change that 16 grams of urea into moles of urea. And we can do that by using the molecular weight that we were given, in this case, 60 grams per mole. That allows us to convert the 16 grams into moles of urea. And then we have 39 grams of solvent, 39 grams of water, and we need to convert that grams of water to kilograms of water. And we do that by sliding the decimal point over 3 places to the left. And so that means it's 0.039 kilograms. We go ahead and do that calculation, and we get 6.8 molal, 6.8 moles per kilogram of water. Number 9, what's the molarity of sodium chloride in solution that is 13% by mass sodium chloride and has a density of 1.10 grams per mil? So we want to get a value of molarity, which we know is moles per liter. So it's moles of solute, in this case, moles of sodium chloride per liter of solution. So we know we need to get, if we have 13% by mass, we know that if it's a percentage like that, we can say we have 13.0 grams of sodium chloride per 100 grams of solution. So we start with saying we're going to convert our 13 grams of sodium chloride into moles, and we do that by using the molecular weight. That's the 58.453 value, molecular weight of sodium chloride. So now we have the grams converted to moles in our numerator. In the denominator, we want to take that 100 grams, because remember we said since it's percent, 13 grams of sodium chloride per 100 grams of solution. So we have 100 grams of solution, and we want to convert that to liters of solution. we were given the density of this sodium chloride solution, and we were told it's 1.10 grams per mil. So we can use that 1.10 grams per mil to convert our grams into milliliters. And then we can use the relation of 1,000 mils equals 1 liter to then convert the milliliters into liters. And so then our final units will be moles per liter. And if we do the calculation, we get a value of 2.45 molar. And then the last one, number 10, we're told we have a mixture containing 41 grams of an unknown non-electrolyte and 660 grams of water. And this has a freezing point of minus 1.34 degrees C. We're given KF value of 1.86 for water. And then what we need to find is what's the molecular weight, grams per mole, of the unknown solute. So for these types of problems, we note we have our formula of delta TF equals minus I times KF times small m. The small m, remember, is molality, which is moles per kilogram of solvent. We know that water freezes at 0 degrees C. So if the freezing point of this solution is minus 1.34, then we know that difference, that delta TF, 0 to minus 1.34, is minus 1.34 degrees. We were told that it was a non-electrolyte. So if it's a non-electrolyte, that means the compound doesn't dissociate. So our I value is just one. Each compound, each molecule is one particle, so to speak, because nothing dissociates. And then our KF value we were given is 1.86. So we have 3 of the 4 variables in our equation known. The one we don't know is molality. So we'll go ahead and we'll solve for that. And we get 0.20 molal. And remembering that molality is moles per kilogram of solvent. So if we go back up and look at the problem, we were told that we have 160 grams of water. So that's the grams of solvent that we have. Molality is moles per kilogram of solvent. So if we rewrite that, we have our 0.720, which we just calculated. We know that's equal to moles of the unknown divided by the kilograms of the solvent. And 160 grams of water is equal to 0.160 kilograms of water. What that allows us to do then is solve for the moles of the unknown. So if we solve that equation for moles of unknown, we get 0.1152 moles of the unknown. So now we're at the point where we still want to get to molecular weight. The molecular weight is grams per mole. We get molecular weight is grams per mole. And what information do we have now? We have moles of the unknown, which is the 0.1152. But we also, if we go back to the question, we see that we have grams of the unknown, and that's 41.0. So if molecular weight is grams per mole, we can take that 41.0 grams and divide it by 0.1152 moles. And that's what we do down here at the bottom. So we have our 41 grams divided by 0.1152 moles, and we get a value of 356 grams per mole as our molecular weight. So a couple comments I'll make about this question is, if you think about what molecular weight of a compound is, we calculate a molecular weight of a compound by adding up all the atomic weights of the elements, of the atoms that are in that compound. And if you think about it for a second, the lowest molecular weight, lowest atomic weight rather, that we have is hydrogen at 1. So if we look at our choices on the multiple choice answer here, the 0.720 and 0.355, it'd be pretty difficult to have a compound that had a molecular weight less than 1. So you could kind of rule those two out just on the basis of that, even before you started doing the calculation. The 4.74 value, that's a pretty small molecular weight, so that one's a little more unlikely as well. So really then, if you're thinking about the problem, it's 283, okay, that's a reasonable molecular weight. 356 is also. So it really kind of came down to those two values as the answer. And then to get the right one, you'd have had to have done the calculation correctly. But the only reason I'm saying this is that sometimes if you're not totally certain how to do the problem, and it is a multiple choice question like this, you can kind of rule out some of the answers just by thinking a little bit about what you're being asked to find. And like I said, in this case, you're asked to find a molecular weight, and you're not going to have a molecular weight that's below 1. So that's one way to kind of think about if the path you're on and getting the answer is correct or not, is think of that kind of stuff too as well. Okay, any questions about the quiz? Okay, so as I said, next Tuesday we'll have an exam, and it'll cover stuff like this, the chapter 13 material, and then it'll cover the chapter 14 material that we're going to start on and continue on now. So let me pull that up. Okay, so hopefully you can see the chapter 14 slides. If not, let me know, but I will assume that you can. So here's where we left off last lecture. Is we talked about plotting rate data and talked about how you can draw the tangents and get instantaneous rate values and things like that. You can also get that rate at the initial rate, the T0 rate as well. So what we're going to do today is we're going to continue on our discussion with regards to rates. And when we talk about relative rates, when we talk about reaction rates, we don't necessarily get the same rate for each reactant and product. And so you might or you might not. And the rate is dependent on stoichiometry. And so if we go back and look at this reaction that we were talking about last week, where we had butyl chloride, C4H9Cl, reacting with water to give us butanol, which is C4H9OH, plus hydrochloric acid. So we use up the reactants, and then we make the products. But what we see here is our stoichiometry on this reaction is the molar stoichiometry is 1 for each of our reactants and products. So if we write that rate, we see that we would write rate is equal to the change in the butyl chloride concentration divided by the change in time, and it's negative out front of that relationship. And that's because we're using up the butyl chloride. So in other words, the butyl chloride concentration is going to be decreasing. The C4H9OH, the butanol concentration, that doesn't have a negative sign, that has a plus sign in front of it, or an implied plus sign, because that's what we're forming in the reaction. So in our reaction, we'd be using up the C4H9Cl, and we'd be making C4H9OH. So we said that the rates go along with the stoichiometry. And so in this case, it was 1-to-1, but what if it's not 1-to-1? So if we just write a general reaction as A plus B forming C plus D, and then the lowercase a, b, c, and d are the stoichiometry values. So in other words, the number of moles of each of those that are involved in either the reactants or the products. Then the way we would express that rate equation would be, for the A component, it would be 1/A, and A being the small a that you see in front, that coefficient. And B would be 1/B, C would be 1/C, D would be 1/D, times that change in the concentration divided by the change in the time. Note again that we have negative signs in front of the A term and the B term, and that's because those are the reactants, so that's what's being used up. And then we have plus signs in front of the C and D terms because those are the products, so that's what's being formed. So that minus means it's going away, it's a reactant. The plus means it's a product. The concentrations are going to be increasing. So in general, if it's not a 1-to-1 reaction, so in other words, the reaction stoichiometry isn't just 1 across the board, then if you have the coefficients in front of the reactants or products, then the rate for that reactant or product would take into account 1 over whatever that coefficient is. Down below, there's an example of where you have O3 converting to O2, and you have 2 moles of O3 converting to 3 moles of O2. So if we were to write rate expressions for that reaction, we would say the rate is equal to minus 1/2 times the change in the O3 concentration divided by the change in the time. So that 2 was the coefficient, coefficient in front of the O3. So that's why we have 1/2 there. And then for the O2, it would be 1/3 because we have a stoichiometric coefficient of 3 in front of that O2 molecule. And so it's 1/3 there. So if it's 1-to-1, it's basically 1/1, which is just 1. If it's not 1-to-1, then you take whatever that coefficient is in front of the molecule in the balanced equation. Remember, we have to balance the equation still, and then it would be 1 over that value. So how do we determine the concentration effect on rate? We talked before that concentration impacts the rate, and that kind of makes sense because if you got more molecules in there, the more likely that they're going to collide and react together and things like that. So how do we determine what that concentration effect is? The way we do that is experimentally, and the way you would run the experiment is you would take one of the reactants. Let's say you have 2 reactants. You would take one of the reactants and you would hold its concentration constant. And then with the other reactant, you'd run a series of experiments where you varied the concentration of that second reactant and then measured the rate for each of those experiments. And then by getting that, you would then start to get a feel for that reactant, how does its concentration impact the rate of the reaction. Then to see how the other reactant impacted the reaction, you would do the opposite. You would now hold the other reactant constant And then the second one that had been constant before, you would vary its concentration and see what the impact was there. So to understand this effect of the concentration on the rates, you gotta do experiments, you gotta run reactions. And so just to kind of show you an example of what that would be like, let's take a look at this example. So we have ammonium ions, NH4 plus, and nitrite ions, NO2 minus, reacting together. And so in the first three experiments, we are keeping the NO2 minus, the nitrite concentration, we're keeping that constant at 0.2 molar. The ammonium ion concentration is varied in each of the experiments. So in the first one, it's 0.01 molar, the second 0.02, and the third 0.04. So what we're doing in each of those is we're doubling the concentration of the NH4 plus. If we look over on the right-hand side of the table, what we see is we see that the rates for each of those are doubling. So we double the concentration from 0.01 to 0.02. The rate goes from 5.4 to 10.8 times 10 to the minus 7. We doubled that concentration again from 0.02 to 0.04. And we see once again that we get approximately a doubling of the rate as well. So we have a feel now for how the concentration of the NH4 plus impacts the rate. Then what we would do is we would do the same thing with the NO2 minus concentration. So let's take a look though, before we look at the second one, let's take a look at what this means in terms of doubling the concentration of the ammonium ion, resulting in a doubling of the reaction rate. So if we set up a ratio of rate 2 to rate 1, we said that doubles. So we said that that's a factor of 2. We also said that we were doubling the concentration. So if we ratio those, it's 2. So what it's saying is if we're trying to figure out the order of, in this case, the ammonium ion, the NH4, we would take that ratio of the rates, which was 2, and that's equal to the ratio of the concentrations raised to some power. So 2 equals, the concentration ratio was 2, and then 2 to the what gives us 2? Well, 2 to the 1 power gives us 2. So that tells us that the order is 1. It's a first order reaction with respect to NH4 plus. So basically, if the rate doubles when the concentration doubles, that reactant has a rate order of 1. As I said, so in that first 3 experiments, we kept the NO2 minus concentration constant, varied the NH4 plus. Experimentally, if we want to now figure out what the rate order is for the NO2 minus, we need to do a similar experiment. So here we keep the NH4 plus constant at 0.2 molar. So we have the NH4 plus constant at 0.2 molar. We change the NO2 minus concentration from 0.02 to 0.04 to 0.08. So once again, we're doing that doubling where we double it from 02 to 04, and then double it again from 04 to 08. And we see what the impact is of that doubling of the nitrite concentration on our rate. And we see once again, we get essentially a doubling of concentration. We go from 10.8 to 21.6 times 10 to the minus 7. And then we go from 21.6 to 43.3 times 10 to the minus 7. So we see a doubling, similar to what we saw when we varied the NH4+. So we would do that same kind of evaluation like we did for the ammonia. And we would see once again that the rate order for this compound, the NO2 minus, that it's 1 as well. So in this case, each of these reactants has a rate order of 1. Now that we know the rate order for each of the reactants, what we can do is we can write a rate equation for the reaction. And that's what we have at the bottom here. We have the rate would equal K. K is the rate constant. We'll talk more about that. But rate equals K, which is the rate constant, times the ammonium ion times the nitrite ion. They're both to the power of 1, both of those concentrations, because our rate order is 1 for each of those reactants. So in this case, rate order for each reactant is 1, rate order for the total reaction is 2, because we have 1 plus 1. As I mentioned, the reaction order, the rate order with regards to each reactant is 1. Their first order, we call that first order with respect to each of those. But overall for the reaction, because we have 1 plus 1, is the order is 2. So the reaction is second order. Reactants are first order. Reaction total is second order. I mentioned that K is the rate constant. One of the key things about the rate constant is that it's temperature dependent. So usually we think of constants as not changing. For the rate constant, when we're talking about these reaction rates, you do need to make sure that the rate constant is for whatever the temperature it is that you're operating at, because the rate constants tend to increase as the temperature increases. So the thing to remember, though, is that when we write these rate equations, so like here we wrote this rate equation here with the rate constant and the concentrations, that is not based on stoichiometry. The previous stuff we talked about, we said we can figure stuff out based on stoichiometry. So go back here for a second. Remember when we were writing rate equations this way, that was based on stoichiometry. When we use the rate equations that we just are talking about calculating here, where we have the order of the reaction, okay, that's the 1, implied 1 on the concentrations here, and has the rate constant. When we have those, it may or may not be the same as the balanced equation. The only way to know what it is to do experiments like we just kind of highlighted in these 2 examples, of where you keep one of the reactants constant and vary the other and see what happens to the rate, and then do the calculations to get the order. And then you can go and figure out if there's any exponents on the concentrations. So, and let's take a look at a couple examples to show you what I mean. So in this first example, N2O5 going to NO2 plus O2 gas, what we see is that we have coefficients of 2 in front of the N2O5. And so you might expect that this would be K times N2O5 squared, but it's not. So whenever the experiments were done to assess the impact of that concentration of N2O5 on the rate of the reaction, the data must have shown that it was a simple doubling type of thing like we saw on the example. So it wasn't, so we don't have a squared value here. It's a first order reactant. And so even though the stoichiometry says 2 moles of it are involved, the rate order is just a first order. So there's an implied 1 there. We look at H2 plus I2 to form HI, and there the stoichiometry is 1 mole to 1 mole, and our rate equation has first order with respect to H2 and first order with respect to I2. So in that case, it does match the stoichiometry of the reaction. And then in the third example, CHCO3 plus Cl2, those reactants, we see that when we look at its rate equation, we have CHCO3, but then the Cl2 concentration is to the 1/2 power. So once again here, when the experiments were done, it showed that you didn't have orders for the reactants that match the stoichiometry of the balanced equation. So orders for the reactants and orders overall for the reaction, once again, don't necessarily match the stoichiometry of the equation. Okay. When we talk about the rate constant, there's a rule of thumb that if you have a rate constant that's 10 to the 9th or larger, then usually that's considered to be a fast reaction. If it's 10 to the 9th or lower, then it's considered slow. And so why would that be important to have a ballpark idea of if the reaction is fast or slow? Well, if you have a slow reaction, you probably want to do something to speed it up because you don't want to sit around all day trying to get the reaction to go. And so, we had talked about that rate constants are temperature dependent. So you could increase the temperature of your reaction, and that might help. That might increase that rate constant and thus increase the rate. There's some other things you can do. We'll talk about catalysts a little bit later in the chapter. Catalysts are a way to increase the rate of the reaction. So if you know you have a slow reaction up in the beginning, then you can start thinking about things that you can do to kind of speed it up. So that's why it's nice to kind of have some information and just ballpark information about is the reaction fast or not. Okay, let's talk a little bit about first order reactions, second order reactions, and start discussing what that means. And so a first order reaction means that the rate depends only on one reactant, and that reactant is a first order reactant. And so the rate law you can see written as rate equals K, or rate constant, times the concentration of that material, that reactant. It's a pretty simple formula to write. And so you have examples of reactions where even if you have other reactants in there, it's only dependent on that one reactant. So one of the things is, how do you determine if something is what is it first order or not? Well, you need to do the experiments, kind of like what we talked about a few slides ago, where you vary concentrations and things like that. But one of the big things you can do is you can plot the data, and depending upon what you have to do to get the data to be a linear plot, that is a real simple visual way of telling you if you have a first order or second order type of reaction. And so what I'd like to do is walk through that a little bit and show, first of all, would like to show how you rearrange the rate expressions to get the data presented in a way that you can easily plot it and then determine if it's linear or not, and then thus is it first order, second order, et cetera. As I go through just kind of how these equations come about, certainly, follow along and make sure you understand what I'm doing, but that's not the key takeaway for it. The key takeaway is to just kind of the end result and then how that end result is used. So certainly, I hope you understand how we get to these final equations, but more importantly is being able to use the equations to determine order of reactions and things like that. So we go back to, we've been talking about first order. So we go back and we say rate equals K times A. So the concentration of the reactant. But we also could say that rate equals minus delta A over delta T. So those were the two ways that we had to express rate. Well, since they're each expressing the same thing, we can set them equal to each other. And so we have the rate constant times the concentration of A equals minus the change in the concentration of A over the change in time. We can rearrange that to where we have both of the concentration terms on the left and then our rate constant and our change in time over on the right-hand side. If you think back to calculus, you can use some of that information when you talk about having changes, and you can then rewrite the equation as below. And so you can have natural log times concentration of A at a particular time t divided by the concentration of A at the start equals minus K times the time. And this time value is the time at which this concentration with the sub T on it, the T subscript on it, that's the time value that you use. The other thing I'll mention is remember that this is a natural log. So that's why it's ln instead of lg or log. And so make sure that you know how to use do natural logs on your calculator or the computer or however you're doing it. So don't get confused with log, base 10 log, which is the log, versus the natural log, which is ln. So make sure you know that on your calculator. Okay, so the other thing I want to point out is, so we have this formula here. We can further rearrange this to have natural log of A sub t minus natural log of A sub 0 equals minus kt. Because remember, when you have these natural logs divided like this, to separate them out, it's natural log of the numerator minus natural log of the denominator. So that's all we've done here, is broke them out that way. We can further rearrange this. We can bring this natural log of A over to the right-hand side of the equation. And we wind up with natural log of A sub t equals minus kt plus natural log of A sub 0. What's key about this, and the reason why you would want advantage to rearranging things to get to this form of the equation, is that this sets us up to look like the equation of a line. And remember, generically, the equation of a line is y equals mx plus b. If we look at what we have up here, we have natural log of A sub t, that's lining up with y, the y variable. We have minus k times t. T is our x variable, time. minus K would be M. Remember, M is the slope of the line. And then natural log of A sub 0 lines up with B, and B is the y-intercept. So if we have our data expressed like this, and we have a line that matches this, then what we have is we can go ahead and we can plot on the x-axis time values, and on the y-axis natural log of A at those different times, that concentration, and we should get a straight line. So the other thing we get from that, if it's a straight line, then that tells us it's a first order reaction. So that's good to know. Nice, easy visual way of determining if it's a first order reaction. The other thing we can get from that is, I said in this configuration, minus K is the slope of this line. So if we go ahead and do our line fit and then calculate what the slope is, then we have found what minus K is, and we can just simply change the sign and we have a K value. So arranging it this way allows us to do a few things. One is we can do this plot of natural log of A at the different times on the y-axis and time on the x-axis. If it's a linear plot, plotting the data that way, it tells us it's a first order reaction. And then once we know it's first order, we know from our best line fit equation that the slope is equal to minus K. So it allows us to get that rate constant. So as I said, we can do that plot and we can get the rate constant because the slope is equal to minus K. Let's talk a little bit about something called half-life. So a term that's used in reaction chemistry quite a bit is half-life. And half-life is simply the amount of time it takes for half of the reactant to be used up. So if you started with 10 molar of a reactant, you'd be wanting to know how long did it take me to get from 10 molar to 5 molar. And that time that it would take would be known as the half-life. And this is kind of interest because once again, it feeds into reaction rates and how long does it take for a reaction to occur and things like that. The interesting thing about half-lives is that you can constantly be recalculating them. So if you go from 10 to 5, then you can recalculate it from 5 down to 2.5 and et cetera, et cetera. So let's see how we would calculate a half-life for a first order reaction. So once again, as we did before, we're going to do some manipulations of formulas. And so, please follow along and kind of hopefully you'll understand the manipulations we're doing. But really the key thing is to focus on the end result. But I want to walk you through how we get to that result. So hopefully that'll make sense to you. So here's our formula that we had for first order reaction. This was our y equals mx plus b type of setup. And so if we're saying that half-life is the time it takes for half the reactant to be used up, we can take this A term on the left-hand side and we can replace it with the initial concentration divided by 2, because that's what we said we're trying to find. The concentration that we started with, how long until it became half. So we can take that initial concentration and divide it by 2 and substitute that in for the A term above. Then the other term we can change is the time term. The time that we want is the time for the concentration to be half. So we're going to call that T with a 1/2 subscript. Now, if we go ahead and do some rearranging, so in other words, we get once again, we get the concentration terms both on the same side of the equation. We get this next relationship. And then if we go back here a bit, remember we can go ahead and then rearrange again. And now we have A sub 0 divided by the ratio of A sub 0 divided by 2. If we rearrange this part that's in the parentheses, what we see is the H sub zeros cancel each other out. And so what we wind up with is natural log of 2 equals K times the half-life time. And then if we want to solve for the half-life time, if that's what we're trying to get, we can then simply rearrange this. And so the natural log of 2 is equal to 0.693. So we have 0.693 divided by the rate constant. What's interesting about this is for the half-life, we see that the half-life time is not dependent upon the concentration for a first-order reaction. So that's kind of what an interesting takeaway from working through these rate relationships and boiling it down to this half-life rate being equal to 0.693 divided by the rate constant. So it does depend on the rate constant. It doesn't depend on the concentration of the reactant. So let's talk about second order reactions. And so sometimes it only depends on the reactant in the second power. And these are ones that are second order reactions. The example we're going to go through is just where we have one reactant that matters, and it's a second order reactant itself. If you recall, we talked about before that you can have second order reactions where you have two first order reactants. That gets a little more complicated to figure that stuff out. So the purpose of what we're doing today is we're just going to focus on a second order reaction that has one reactant, and that reactant is second order. So rather than K equals A to the 1 and B to the 1, we're just going to do K times A squared. Okay, so just as we did before, we can kind of go through and look at our initial rate expressions. So rate equals K times A squared, because it's second order, so we know that superscript is 2. And then rate equals minus delta A over delta T. We set those two equal to each other as we did before. We get our next equation here, next relationship here. We further can shift things around, getting all of the concentration terms on the same side. Once again, there's some calculus that goes into this to get rid of the deltas. And we wind up with 1 over A equals 1 over A initial plus KT. Probably should rewrite this a little bit and bring the KT over to the left. So it's KT plus 1 over A. That will get us to where it looks a little bit more like the Y equals MX plus B presentation like we had before. So in this case, the Y term would be 1 over A concentration equals MX would be, M would be the K. So the slope of the line would be the rate constant. And then T would be the X variable. And then plus 1 over A sub 0. So that initial concentration. And so that 1 over the initial concentration, that would be the B term in our Y equals MX plus B setup. So that would be the Y-intercept in our plot. So what's interesting about this is if we plot 1 over A on the Y-axis and T on the X-axis, we should get a straight line. And the other thing we would know from that is if we get a straight line, then the slope of that line is equal to K, the rate constant. So by plotting the data this way, the concentration and time data this way, what we can do is we can see if it's linear or not. And if it's linear, then we know we have a second order reaction. And then once we know it's linear and it's second order, we can get from the slope of that line, we can get what the rate constant is. So if we compare the two, the first order and second order reactions, we see when we did the first order that the linear plot, we had natural log of the concentration on the y-axis and time on the x-axis. If we plotted our data that way, then we got a straight line, and that would tell us that's a first order reaction. If we plotted it that way and it wasn't a straight line, then we would know it's not first order. So then maybe we would try second order plot. And so we would then plot the data with 1 over the concentration versus time. If that plot then was linear, then that would tell us that we had a second order reaction. So it's pretty neat that by taking the data that you get, you can go ahead and determine, so you run your experiments, you have your data, you see how the concentration is varying versus time in the reaction. Go back and plot that data, and depending upon what you have to do, what format you have to plot in to get a linear plot, you can get whether it's a first order reaction or a second order reaction. And then it also tells you, based on that, by having the slopes of the lines, you can get rate constants for those reactions at that temperature as well. So that's what I was saying, is that by taking some of these rate expressions that we learned about and combining them and then rearranging them, we can get them into formats that represent that linear format, that linear plot, and then plotting the data using the appropriate variables. And then we can see if we have first order or second order reactions that we're dealing with. And here's just an example of what the plot would look like. So in this case, we see that the NO2 decomposition data was plotted versus time. So in the top one, we have natural log of NO2 on the y-axis and time on the x-axis. And we see that's not really a linear plot. It's kind of got a curve to it. In the bottom, we have 1 over the NO2 concentration. On the y-axis and the x-axis, we have time. And we see when we plot that, it's a straight line, a nice straight line. So we go back here and we said, first order, if it's natural log versus time linear. Second order, if it's 1 over A versus time. So 1 over A, 1 over the concentration is linear. It's not linear for natural log versus time. So that tells us that it is a second order. So then we could, as I said, we could go ahead and calculate out the slope of that line, and the slope would give us information about what the rate constant is. Any questions about the first order, second order, and the plots and that stuff? Okay. So let's take a look at kind of the rearranging for the second order to see how that impacts the half-life. Kind of like what we did on the first order. And so once again, we take our line equation type approach here with the y equals mx plus b, and then we start rearranging stuff there. And we get to the point of, after we do all of our rearranging and do a little bit of calculus, we have t 1/2. So our half-life time equals 1 over the rate constant times the initial concentration. So what the key thing here is, one is the final formula, but the other key thing is that when we looked at the first order reaction, there was no concentration term in this formula. It was just that natural log of 2 value and then the rate constant. What we see in second order reactions is that half-life time is dependent upon the concentration that you're starting with. And so we see that because we have a concentration term in the denominator. So first order reactions, that half-life is not dependent upon the concentration of the reactant. Second order, it is. So that's another difference between first order and second order reactions. There is something called a zero order reaction, and that means that the concentration, the rate rather, is not dependent upon the concentration. So no matter what the concentration is the rate stays the same. And if we present that in that linear type of plot form, y equals mx plus b, we see that y is the concentration at a particular time, minus k is the slope, time is the x variable, and then the initial concentration, a sub 0, that's the y-intercept. And so in this case, if we do this plot of concentration versus time, we should get a linear plot, and then the slope is equal to minus k. So once again, a different way we would plot data than for first order or second order, but yet based on how we plotted that data, we would be able to tell if it's zero order, first order, or second order. Okay, there are a few homework problems I'd like you to work on. So what I'd like to do, though, is take a few of them and go through them in class, just so you can kind of see some examples of how to do some of the problems. Before I go through the examples, does anyone have any questions about anything I've talked about so far? Okay. So the first problem we'll take a look at is 14.31. And we're given a reaction, CH3Br, so methyl bromide plus hydroxide OH minus, to give us CH3OH, which is methanol, plus Br minus. And we're told that the rate law for this reaction is first order with respect to both CH3Br and OH minus. So each of those reactants are first order reactants. So first order reactants for each of those, the overall reaction would be second order because we'd have 1 and 1 is 2. And then we're told, we're given some concentrations for the methyl bromide, 5 × 10⁻³ and the hydroxide, 0.05 molar. And we're told that with those concentrations and the temperature being 298 Kelvin, that the rate of the reaction is 0.0432 molar per second. So they ask us to calculate the rate constant. So we think about what information we have, and so we have a rate, and we know we can express rate as being equal to the rate constant times the concentrations of the reactants raised to whatever power their order is. So the order, we were told, is first order for both CH3Br and first order for OH minus. So our concentrations are simply those concentration values we were given. We don't have to to square them or anything like that because they're first order. K, the rate constant, is what we're trying to determine. And then finally, the rate at this temperature we were given as 0.0432 molar per second. So if we go ahead and solve that equation, we get 173 m to the minus 1 s to the minus 1. And so that rate constant units are such that we know our rate is molar per second. And so we need that rate constant to be able to cancel out units of what we have with our concentration. So we'd have a molar and a molar. So we have to cancel out in a way so that we get that molar per second. So that's why the units there are molar to the minus 1 and seconds to the minus 1. So we have our rate equation. We've figured out our rate constant. And then we're asked, if the hydroxide concentration is tripled, what happens to the rate? Well, if we look at that, we see over here our hydroxide is this 0.05 term. If that increases by threefold, then there's a direct proportionality to the rate. So if that increases by 3, this is going to increase by threefold, okay? Then the next question is if each of them are tripled. So in other words, if the CH3, the methyl bromide is tripled and the hydroxide is tripled, what's that going to do to the rate constant? Well, if each of those terms increase by 3, 3 times 3 is 9. So our overall rate is going to be increased by a factor of 9. Okay, let's go to the next one. 14.33. So in 14.33, we're given this equation of where hypochlorite ion and iodine ion react to give us OI minus and Cl minus. And then we're given some concentrations of the two reactants in each experiment. And then we're given what the rate was determined to be for each of those concentrations. And so this is similar to the example we went through of where you're trying to determine some of this stuff. You keep one of the reactants constant and vary the other one, and then do vice versa to see the effect on the other. And this will allow us to figure out if we have first order or not. And so if we just take a look at this for a second, if we look at the OCl minus, we see that in the first experiment, it's 1.5, and the second is 3.0 times 10 to the minus 3 is the concentrations. So we've doubled the concentration of that. The I minus concentration we've held constant at 1.5 times 10 to the minus 3 for the two of them. If you do that, you see that the rate increased by approximately a factor of 2. So that tells us you double the concentration of OCl minus, you get a doubling of the rate. So that's telling me that I have a first order type of situation. Let's take a look at the I minus. If we look at the first experiment and the third experiment, in those experiments, we've held the OCl minus constant at 1.5 times 10 to the minus 3. And so we varied though, so we've kept that constant, but we varied though the I minus concentration. In the first one, it's 1.5, and this third one, it's 3 times 10 to the minus 3, so we've doubled that. So let's see what happened to our rates. Our rate went from 1.36 to 2.72 times 10 to the minus 4th. Once again, we see that doubling of the rate as we double a concentration. So what this tells me is that since we have doubling the concentration of each reactant, that doubled the rate, we know that each reactant is first order, and we can write this rate equation below. So we say rate equals the rate constant times the chloride ion to the first is a first order, and the I minus is a first order. So now we've got a rate equation that we can work with. We figured out the orders of these based on our experimental data that we generated. Then the next question on this is, go ahead and calculate a rate constant. Well, if we just go back to the data we were given, we can take any one of these three scenarios because we've got concentrations and we've got a rate. So I'm going to take the first one where they're both 1.5 times 10 to the minus 3, and then the rate is 1.36 times 10 to the minus 4. So if I go ahead and plug those values into my rate equation, I have 1.36 times 10 to the minus 4 as my rate, and that's equal to the rate constant, which is what I'm trying to determine, times the concentrations of the two reactants. And so that's 1.5 times 10 to the minus 3 times 1.5 times 10 to the minus 3. I go ahead and solve this equation for K and make sure my units work out so that I wind up with molar per second on each side of the equation. And I get a value of 60 as for my rate constant. Then the final question is on part C, we're being asked, well, now if the concentrations are different than one of the concentrations that we were given, in this case, 2.0 times 10 to the minus 3 for the OCl minus, and 5 times 10 to the minus 4 for the I minus, what is the rate? Well, remember I said the rate constant is the same unless you change temperature. So we've just calculated a rate constant and we've not changed temperature. So we can use that rate constant value, that 60 value that we calculated in part B, and then we can plug in our new concentrations that we were given and do those calculations and then get a value of 6 times 10 to the minus 5th molar per second as our rate for the reaction. Okay, so any questions about either of those? All right, let me move on to another one then, number 14.41. And here we have gas phase decomposition of SO2-Cl2. So that SO2-Cl2 decomposes to SO2 plus Cl2. And we're told that it is first order with respect to SO2-Cl2. And at 600 Kelvin, the half-life we're told is 2.3 times 10 to the third seconds. So the first thing we're asked is, what's the rate constant at this temperature? Well, some key things here. One is we needed to know the order. And once we're told that it's first order, that tells us which of those half-life formulas that we want to use. And for this problem, we get to use the simpler one. We get to use T half-life equals 0.693 divided by the rate constant. So if we go ahead and plug in the half-life time, which was 2.3 times 10 to the 5th seconds, into the T1/2 value, now we can solve for K, and we get a value of 3.0 times 10 to the minus 6 as inverse seconds as our rate constant. In part B, we're told that at 320 degrees C, the rate constant is 2.2 times 10 to the minus 5. And we want to calculate out what the half-life is at this temperature. And so we go ahead and put in our value for the rate constant we were given at this temperature, 2.2 times 10 to the minus 5. And we do the calculation and we get a value for the rate of 3.2 times 10 to the 4th seconds. So what we see is we do see that we do get a difference in the rate because of different temperatures. Okay, any questions about any of those problems? So what I would ask is that you go ahead and spend some time working on the homework problems. The answers, as usual, are posted on Canvas if you get stuck on something. One last thing I want to just go through a little bit is that talk a little bit about factors that impact the reaction rate. Temperature is one. We've talked about that a little bit. But some of the others are frequency of collisions. So for reactions to occur, the molecules have to be in contact with each other. They have to have a collision, basically. So how often those collisions happen increases the odds of the reaction being successful. But the other thing that happens is you think about it, usually in reactions, what you're having some bond breaking of certain molecules and bond forming and things like that. In order for the right bonds to be broken and then the right bonds to be formed, the molecules have to be oriented appropriately when they collide so that the right things are hitting each other. And so number of collisions, orientation of the molecules, both very important. And then the final thing is there takes a certain amount of energy for the reactions to take place. And this leads us to something that we call the activation energy. And the activation energy is having the right amount of energy in the system so that the reaction can occur. So do you have enough energy in there to break the bonds? If you need energy to form bonds, do you have the right energy? Things like that. But definitely for breaking bonds, you need energy. And so there's a lot of work that's done to understand what that activation energy is. It's usually linked back to some intermediate reaction that takes place in the reaction mechanism. And I think with that, we will end for today, unless anyone has any questions. Okay, thank you.
Thank you.